All right, so tonight we're going to go over calculus and how it relates to gradient descent and using gradient descent to perform linear regression. So the outcomes of tonight's study group are to be able to calculate derivatives for any given function, to understand partial derivatives, to understand and implement gradient descent in order to perform linear regression, and also just to gain some more experience working with NumPy arrays. So to start off, what is a derivative? So the best way to kind of show this is to plot a function here real quick. So this is basically x squared. So if we have this function here, can either of you tell me what the slope of this function is?
Would it be 2x?
So you're getting a little ahead of it, but yeah, that would be if you did the derivative. But so if I get my line tool here.
It should be x squared, right?
So I guess what I'm talking about is if I pick a point, like the slope is like tangent to that point, and basically I can keep doing this all the way down. So what I'm getting at is the slope changes. So if, for example, we just had like a line like that, the slope's going to be constant. So if we wanted to plot this slope, it would just be a line straight across. But when we have a curve, if there's a quadratic formula or anything higher, the slope's going to change. So we need a way to be able to model that slope and to be able to plot it. And this is where derivatives come into play. So with derivatives, there's a couple rules that let you figure out how to calculate them. So the first is the power rule. So we can take that x squared, and using the power rule, the derivative of x squared would just be 2x. So the idea is that you take the power, you move it to the front, and then you subtract 1 from that power. So in here, we moved the 2 over to the front. It's now the coefficient. And then this would basically be a power of 1, but we don't write it because it's the power of 1. So another example, if we had x to the 5th, can someone tell me the derivative of this?
5x to the 4th.
Yep. So that's basically the power rule, pretty straightforward. All right, the constant factor rule. So now if we have a number in front like this, basically what happens with the constant factor rule is you can ignore the constant factor on the outside, find the derivative of the inside, so 3x squared, and then just multiply that constant factor back in. So you'd have 15x squared. Or another way to do it is to just move the exponent down and multiply it that way. And then you can just go directly to 15x squared. All right, so the next rule is the addition rule. This one's pretty straightforward as well. It basically says that if we have like x squared plus 2, or x cubed plus 2x squared plus 5x, to find the derivative of this, we just find the individual derivatives of each part and add them together. So we would have 3x squared plus 4x plus 5. All right. And now the chain rule, this is where things get a little bit more complicated. So if we have something like this, if this is our function and we want to take the derivative of it, we have to do something kind of tricky. We have to basically take the derivative of the outside part, so outside the parentheses. So if we were just to put like a box over the inside and ignore it, the derivative would just be 2 and then times what's inside the box. So x squared minus 2x. But we didn't address the inside part, so then we also have to multiply this by the derivative of the inside. So then the derivative of the inside would be 2x minus 2. So this would be the final derivative. You could always, multiply it out, but this is basically how you use the chain rule. All right, partial derivatives. So sometimes you have a function that has two different variables in it. So you could have x to the third plus 2y squared. So if you have multiple variables, you can take multiple derivatives. And basically you choose one of the variables and you find the derivative with respect to that variable. So if we want the derivative with respect to x, we basically treat y as a constant and we just focus on the x variable. So we would have 3x squared, and then we just pull down the whole y term. So it'd be 2y squared. Similarly, if we wanted the derivative with respect to y, we would keep the x term as it is, and then just find the derivative of wherever we have a y. So plus 4y. So in that way, you get two different derivatives. It's just with respect to the two different variables in our function. All right, so now time for a quick knowledge check. I have 4 equations here. I'm just gonna ask someone to volunteer and we're just gonna go through each one real quick and just solve it on screen. You can use the annotate function. So do I have a volunteer to do this first one?
I can. Let's see. It's gonna be. This is really hard on a trackpad.
Yeah, you basically need to use a mouse.
There we go.
All right, that looks good. And yep, you could simplify it to like 6x to the 8th, same answer. All right, the next one, Jacob or Bonnie?
I'll do it.
All right.
So, before.
Alrighty, what do we think? Does that look correct? Looks good to me. Oh, and I guess this touches on a part we didn't mention, but it's kind of assumed. If you have a constant value like the +7, that just drops. The derivative of a constant is 0. All right, the third one then. I guess Bonnie, if you're with us.
Yeah, but I feel like I missed a part of this, the chain rule.
Okay, so we can maybe talk you through it. So the idea is that you first take the derivative of what's outside the parentheses,
Mm-hmm. So
and you
that
write
would
that
be
down.
like, do I use the mouse function?
It should be like the annotate up at the top.
Okay. So, can you see it?
Um,
It doesn't work for
no.
me.
You have to let go before it'll let you see.
Oh, like this.
Mm-hmm.
There we go.
It's so ugly. So this whole thing and square.
Mm-hmm.
Yep. And then you just multiply that by the derivative of the inside.
Multiply the whole thing.
Yep.
So I do this. Oh, multiply by 6x plus 4.
Mm-hmm.
No.
Yep.
Okay.
Yep, that's correct. That's the chain
Cool.
rule. All right, and then the last one. Whoever wants to do that, you have to find two derivatives since we have two variables.
Great. I'll do the x.
Okay.
Hold on. And then for partials, do we still get rid of the constant?
Yep.
Okay. So that would be the x derivative.
Yep. Do you want to just write the y real quick?
Yeah.
I think you guys got a hand on this, but still have to go over it.
Okay, so we keep for the first one, we keep the 4y squared.
Yeah, so that you might have came in during this part, but so that first one is the derivative with respect to x.
Mhm.
So we only focus on the terms with x in it, and everything else stays the same.
Okay.
And then similarly for the second one, with respect to y, we ignore the x and derive the y terms only. And yep, that looks like the right answer.
But we got the 8, the constant, we still don't want it, right?
Yeah, you still drop the constant in both cases.
Okay.
All right, any questions on finding derivatives? Nope. Okay. Go ahead and clear that. All right, so now a cool thing about derivatives is what you can do with them. And so if we have our function here, x squared, well, that should be going through the origin, but just pretend it is. So let's say we wanted to find the minimum value of this curve. So where would that be? That would be right here.
Yeah.
So the trick is you can find that if you find where the derivative of the function is equal to 0.
Hmm.
So our derivative is 2x. So wherever 2x equals 0 is our minimum. So in this case, it's just 0. So an x equals 0 because it's x squared and it's centered over the x-axis. But you can imagine if you had another curve that was maybe out here, if we took the derivative to find the minimum, it would give us this value of x here. So this is an important property of derivatives because there's a lot of times where we want to minimize some function or the value of some function. So where this comes into play is what's known as the cost function. So the cost function is also sometimes called the loss function. It's basically some measure of error, some equation that tells us how good or bad of a job our model or whatever we're doing is doing performance-wise. And we're basically trying to minimize it. So you can see how we'd want to involve finding the derivative of it. So in the case of like a linear regression, our cost function could be the mean squared error, because that's ultimately what we're trying to minimize. We want to minimize the squared average distance between all the different points. So this would be the formula for mean squared error here. It's just 1 divided by the number of data points, and then that's times the sum of all the squared differences between our actual and predicted values. So now bringing in gradient descent. See if I can bring this up. All right, so the basic idea with gradient descent is we have plotted here our cost function. So it could be mean squared error, it could be something else. We're trying to minimize it, so to find the bottom part where it reaches the lowest value. To do that, we have to find the derivative of it and then set that derivative equal to 0, and that would be where we would find the minimum value. So with gradient descent, we basically start off somewhere along the curve. We check the derivative, and then depending on what the derivative is, that tells us how far away we are from the minimum point. And we use that value to slowly move us down the gradient towards that minimum. So this bottom chart kind of shows it here in motion a little bit. So you can see the point started off up here, and then it moves down. You can see that it kind of slows down as we get closer to the minimum. And that's because there's something known as a learning rate that gets factored into the step size. So the step size is how much we move down the gradient each time, how much we shift the values of our terms to try and get closer to that minimum value. And basically, we include a learning rate. We take a small fraction of that step size each time so that we don't end up overshooting that minimum and basically doing something like on the right graph here, where we start bouncing from side to side and we end up actually exploding the gradient and getting values higher and higher instead of slowly approaching the minimum. So this kind of shows how learning rate is going to be important. You need to make sure it's making small enough changes so that it doesn't overshoot the minimum and end up bouncing out of control.
I have a question about that.
Okay.
So I know that we're supposed to multiply, basically, whenever we're trying to get this curve, we're supposed to multiply our step size by a fraction.
Mm-hmm.
What would you suggest in determining the size of that fraction? Would you use the 0.02 every time, or?
So it really depends on like the scale of your data that you're working with. You'll see a little bit later on, we usually want to like normalize the data. And then when it's in like a -1 to 1 scale or a 0 to 1 scale, then usually something like 0.01 is good. But it really depends on the data set. You'll probably have to play around with a couple numbers. I think there are some like unofficial formulas for like finding what might be the best value, but you kind of have to play around with it. If you start off high, you'll know that you're too high immediately, because you'll start getting values that are just higher and higher. So you kind of just have to lower it until it seems about right, so that you don't have to train it for forever, but it does approach the minimum slowly enough.
Okay, so let's say our scale on our data set is like 10 million or something. Then we would want our first step size to be like 100 and then move down from there. But if our data set was between the 1 and 1, we would want a small percentage of that.
Actually, it's the opposite. So if our scale was in like 100,000s or something, we would want a really small step size, because the values we're going to get from our loss function are going to be higher if our scale is really high, because we're going to be farther off from the actual values. But if we're on a really small scale, then the learning rate can be larger, because our errors are going to be much smaller. So our steps are already going to be pretty small.
Okay, thank you.
Yep. Any other questions on step size, learning rate?
Hey, Matt, you mentioned loss function. Can you, what's the difference between loss function and cost function?
They're basically both the same. You'll actually see them used interchangeably. There are probably different definitions for some people in some applications, but really it's the same thing. It's what.
So it's a like mean standard error.
So that's one type of cost function. So it could be anything. If you were doing like, if you were trying to classify whether something is a dog or not, so it's like binary, then in that case you would want something, you couldn't do like mean squared error because it's a binary thing. So you'd have to do like overall like accuracy. So the cost function can really be anything that you're trying to minimize that measures your error.
Okay.
All right.
So basically you want the cost function to be as low as possible.
Right.
Okay.
Yep. And the problem sometimes with cost functions is there's multiple minimum. So there's a couple local minimum, but then there's like a global one too. So if we had something where it's, like this, if we happen to start off here and we start going down the gradient, we might end up at this minimum and up, but really the global minimum for here. So there are some things you can do to kind of prevent this. That'll come into play later on, especially with like neural networks. But for now, your cost function is almost always just going to be a parabola, and you don't have to worry about multiple minimums.
Gotcha. Thank you.
Yep. All right, so now we're going to see this in action. So we're going to start really simple. We just have a data set with 3 points, and we're going to try and do a linear regression on this using gradient descent. So if you can see on here, we have these 3 points. We basically want the line of best fit that's going to look like that, that minimizes all the distances from the points to the line. All right, so this is a lot of code at first. I'm going to kind of walk through how this all works. So to start, we're just going to import a mean squared error function just so we can do the calculation easy. This basically takes in your y true and your y pred and outputs your mean squared error. So to start, we have to initialize our 2 values. So in this case, we have a linear function. So it's y equals mx plus b. So we're trying to figure out what's the optimal value of m and what's the optimal value of b. So we can initially set them both to 0. We're just going to pick a learning rate here. It's kind of arbitrary and kind of just me messing around with like what worked best. But since our data set is small, it doesn't make too much of a difference. I think you could even drop it in this case, but we'll just put it at 0.1 for now. And then we also need to know how many points we have total, and that's just our n. So to start, we're just going to find our predicted value, actually. So we plug in our m and our b, and I mean they're both 0, so all of our predictions are going to be 0. And then we can find the difference in between the true y value and the predicted y value. So before we get to this next part, I need to kind of show you a little bit of a calculation. So if you remember, our mean squared error is equal to 1 over n times the sum of y minus y hat squared. So this is our loss function. We're trying to minimize it. So we need to find a way to find the derivative of this. So one thing we can do is just move the 1 over n inside. Because if we're just dividing everything by n, we can do it either individually or at the very end. So now we have this. We're going to drop the sum for now. We're just going to worry about finding it point by point. So we just have 1 over n times y minus y hat squared. All right, so now something we can do with this to make it easier to work with is break down our y hat into this formula that we had, y equals mx plus b. Because our y hat's just going to be equal to this at any given point. So it's going to be minus our mx and then minus b squared. All right, so now that we have, this is our loss function for one given point. Now we can take the derivative of this. So we have to use both the chain rule and partial derivatives. So I know you're thinking probably x and y are our two variables, so we would do like derivative with respect to x and y, but we're actually going to know our y true and our. So these are going to be constant numbers for each point that we plug into this. So the two variables that we're not sure of their value that we're trying to figure out are m and b. So we need to take the derivative of m, or with respect to m, and the derivative with respect to b. It should be a d down there. Okay, so first with respect to m, we have to use the chain rule because we have this inner part and an outer part. So we'll move the 2 over here and we get 2 over n, and then it's going to be times this inside part. And then we have to multiply it by the derivative inside. So if it's with respect to m, our derivative is going to be minus x. So we could move this around a little bit, and it's basically minus 2 over n times x times, this is our y true minus y pred. So basically y minus y hat, we can just put that back together. So the derivative with respect to our slope at any given point is going to be equal to this here. So something similar for with respect to b, our y-intercept, we multiply the 2 over, and then we have this whole inside part again. And then if we take the derivative with respect to b of the inside part, b is just a single term here, and there's just a minus 1 in front of it. So it's just minus 1. So we can just put it on the outside here. So really, the derivative of both are pretty similar. The one with the slope just has an x term multiplied in there. So now with these two equations for the partial derivatives with respect to our slope and our y-intercept, we have a way of calculating the slope of our gradient and performing gradient descent. So if we go back over here to the code, I basically put in these equations here. So derivative with respect to m is just written here. And so now that sum comes back in because this was just for one point. So we have to sum all of the multiplications of our x values times the difference in our y true versus y pred. And then similar for derivative with respect to our intercept, same thing, just the sum of all of our y differences since there's no x term in the derivative with respect to b. All right. So now the next thing is to modify our m and b in response to these derivatives that we got, and then also taking into account the learning rate. So we basically take our current values and we subtract from them our learning rate times the partial derivatives for each variable. And so that will change both of those slightly. Now if we run this, this is just one pass through. So this should give us a different m and b than our two 0 values. If it would finish loading anytime soon. There we go. All right, so we can see it changed both of them slightly. And then I also just printed out the mean squared error. It's pretty high, so obviously we're not close to the right solution. So what we can do is just comment our m and b being 0 here out, just so it won't overwrite itself each time. And we can just run this cell multiple times. Each time it's performing one pass, one epoch of gradient descent. So you can see over time, the values keep changing. Mean squared error keeps getting smaller. Basically, if we did this a bunch, we would end up at the optimal solution. And I will show that on the next slide here. So this is basically the same code. I just added a for loop. And then I set a variable called epochs equal to 100. So an epoch is basically one pass of gradient descent, calculating the derivatives, updating m and b. So we're going to do that 100 times and then print out that final slope and intercept, and then the mean squared error. So after 100 times, we got a pretty small mean squared error. And then you can see the slope and the intercept values here. And then if we just plot that, we can see that we kind of got the line we would expect here. It probably could be a little bit better if we ran it for like a few more epochs or something, but it's pretty close. Demonstrates basically how to do gradient descent in linear regression. So to look at a little bit more of a real world scenario with more data, we're going to first just make a function called gradient descent. This is basically the same code as before. It's just in function form. It takes in set of x, set of y points, learning rate, number of epochs. It calculates the number of points we have in the data by taking the length of x. And then it's just going to return both the value for m and b, and then the final predicted y values. So that'll just be easier for us to use here in a second. So another example. So we're going to bring in the data set from Monday's class on graduate admission chance. Give it a second here to load. I really do need a faster laptop. All right, so this is the data set you're probably familiar with. So we're just going to look at one of the features in predicting the chance of admission, and I just chose GRE score. So created my x and y there. And now I'm just going to plug that x and y into the gradient descent. I'm going to choose a learning rate of 0.1, and I'm going to choose 100 epochs, and then we're going to see what happens. All right, so you may not be able to see this in the slideshow. Basically, we got not a number for both. We got some big error. Input contains infinity. So what happened was our learning rate was too small, or I mean too large, and we ended up doing that thing like in the one picture where it kind of bounces out of the gradient. So we have to do something different. So in this case, our GRE score, if we go back up to the data frame here, you can see it's in like the 300 range. The chance of admission is less than 1, it's a percentage. So they're in entirely different scales. So the first thing we can do is min-max scale them. So this basically imports the min-max scaler from sklearn. It fits it to the whole data set, just so it's all scaled for us if we want to work with the other columns in a little bit. And then I just recreate the x and the y. So now everything should be on the same scale between 0 and 1. So now if we run it again, I'm going to keep the same learning rate. I'm just going to increase the number of epochs here. And now if we run it, we get a really low mean squared error. And that seems to look a lot better. We didn't error out. We didn't get the exploding gradient. So to compare our results, we can just fit an OLS model from stats models and check the coefficients, and then I'm also going to print out the mean squared error to compare it to what we got with our gradient descent. So if you can see here, so the slope of our way was 0.8, and down here the slope is 0.8, and then our intercept was 0.18 and 0.18. You can see it's a little bit off. We probably still had a little bit more ways to go to reach that minimum, but the mean squared errors were pretty similar. All right. Does anyone have any questions on this so far?
Yeah, so Matt, the first example, when I tried the learning rate of 0.02, the like MSE actually is is larger than learning rate of 0.1. So,
Okay, so
yeah, how can we judge or like know if we should assign a smaller learning rate or a larger one?
All right, so let's see. So you said you did 0.02 for 100 epochs?
Yeah.
Okay, so we got a mean, oh, I have to reset my X and Y, hold on. All right, so this is 0.2, so we got 2.3. And now if you make the learning rate smaller, we get 0.6.1. So basically with the smaller one, it's taking smaller steps. So we would have to increase the number of epochs. So if we put this up to 200, then we get a lower mean squared error. Because see, it's like if you're going down steps, or like if you're like walking towards something, like if you take smaller steps, like it's going to take you more time to get there.
Right. Okay.
So it's kind of a balance between learning rate and epochs. Like you could have a really small learning rate if you just do like 1 million epochs, but that's not very efficient. So it's kind of finding like the right balance. You probably want to minimize the number of epochs, but the closer you get to like that boundary where it might, spin out of control, it gets kind of messy. So
cool.
Yep. Any other questions? All right, so now we're going to do something fun with our activity. So what we've been doing so far is for basically singular linear regression. We have 1x, but what happens if we have more than 1x? So you're basically going to use our gradient descent function that we just made in this lesson, and you're going to modify it slightly to accommodate multiple x features. So x1, x2, x3. So like in the graduate admissions data set, you have all your different features there. So we basically want to be able to include all of those. So I have a couple like guidelines here, things you'll have to consider in modifying the function. It's really only like 3 changes, 3 of the lines. But so your slope, instead of just having one scalar value, like in y equals mx plus b, you're going to have an m for each of your features. So you have like m1, x1, m2, x2, so on and so forth. So you'll have to make your m an array, basically. When you calculate y pred, you're going to have basically like all of your slopes in a vector, and then you're going to have all of your x's in a vector, or in a matrix, and so you can use what we learned Monday with matrix multiplication to calculate y pred that way, so that you don't have to do like a for loop or anything. You can just multiply the 2 numpy arrays together. And then similarly to that y pred calculation, to do the derivative with respect to m, since now you have multiple m's, you'll also have to do the matrix multiplication there. And I have a little note. You want to keep in mind when you multiply matrices, when you do that product, they have to be a certain shape. So you might have to do a little trick to get something to be the right shape. That's kind of my hint there. All right, so that's basically the task, just to rewrite that function to handle multiple features, and then just run it on the graduate admissions data set, compare it to OLS, and then just figure out what you think the best learning rate and number of epochs are. So since there's just 3 of us, I'm thinking we just stay here. You guys can all work on it together. I'll sit back and maybe give you some hints now and then if you need them. All right, we'll go ahead and.
So if you scroll up a little bit. Oh, you start from here. Okay, never mind. So first we plot the data, and we found actually different variables. They have very different scales. So the first thing we do, we transform the data using min max scalar. So make sure they are all in a scale of 0 to 1. And if you scroll down, so basically rewriting this function, we notice that the m, which is the should be a vector vector of values, and the length should be equal to number of features. So, and then so in that case, if we do a dot product of x and m, and plus the constant, we will get our y observation, which is 500 observations. So, and then the y pred will just be x dot sum m plus b. And our y diff is the same as y minus y pred. And so our derivative, the one change we made is to remove the sum, because the dot function already do multiply and sum. So, and the derivative respect to b doesn't change. Yeah, and then we also print out the MSE, the minimum standard error, right? Is that, what's the definition? Mean squared error, sorry. Yeah, and we chose the learning rate of 0.02 and 1,000 epochs. Yeah, do you want to add anything, Beth?
This is the multiple gradient descent method. We compared it to the OLS method that we've been using in the past. We found that we got a mean square error that was a little bit better than the OLS, but at the same time, we didn't also get an R squared error with using the gradient descent method. These would be the M output that we get is the coefficient of the constants, aka the predictors that we're trying to use to determine our target variable. This y pred at the end is just a printout of the last prediction that was made using our for loop here. Yeah.
All right, good job, everyone. So now we have those that array of m's, our coefficients. But since we scaled our data initially, those coefficients are scaled too. So I think Jacob actually got the reverse transformation to work on the coefficients. So if you want to share your screen, Jacob.
All right, so what I did was the same scalar, but just use the inverse transform. And I just passed in the coefficients that I got above into an array and did the reshape for 1 and -1. And it shot out these values here.
And you had to add a 1 at the end, right? Because
Oh, yeah.
we initially transformed on x and y, and so we have to give it the same shape as before.
I forgot about that part.
Wait, so you just manually input all the m value?
Mm-hmm.
You also could just
one here.
yeah, you
Pass.
probably could just append the 1 to like your M array and pass that in, or you can just do it manually there.
Okay, yeah, this even adjusting it for Jacob's code, mine still is broken.
It's a NumPy array, so I think it's a different thing besides append. Let's see, NumPy.
What does the reshape mean?
So you have to do numpy.append and then do pass in your M and then a 1 in brackets maybe.
Append
Let's try that.
1 reshape.
Yeah, same thing.
There we go. So that's how you would do it.
I put a bracket around 1.
Yeah.
Still doesn't work for me.
Yeah, mine's still broken.
Let's see how your scalar set up, Jacob.
I just set it up like this.
Is that what everyone else has?
Yep.
Yeah.
So maybe try running that again, the scaling, and then try the inverse again, like directly after, if it's not working.
Wait, your reshape.
Mm-mm.
Transform. Oh, I think I know what's wrong here. Oh, it's just a bracket I put in the wrong place. So yeah, so your yeah, I now get the result.
All right, but it's not working for you, Beth.
Nope.
Look at a bracket. But now my last value is just 1. I don't know if that's correct.
So it just stayed as a 1 after the transform.
Yeah.
I
After
mean, Jacob's is
transform-
pretty close to a 1. It should probably
Yeah.
stay about a 1. Because we're taking it to the scale of 0 to 1, so yeah, it should probably stay that way. I think it's basically what Jacob has here.
Oh, no,
Python just
actually,
has a way of doing decimal places like that sometimes when it's close to a value.
no, actually the value has not changed for me. So it's the same M.
Oh, so you're having the same problem as Beth. So just double check, like the code's exactly the same.
No. I actually, so on Jacob's screen, he has NP array, open parentheses, open brackets, then the list, and then a closed bracket, and then dot reshape. For me, whenever I run it that way, I get an error that says list object has no attribute reshape.
Okay, so I think you guys are on different versions of either Python or these libraries.
That's what I was thinking.
So NumPy, I think probably in that case is probably different versions for you.
And I forget the way to check that.
Jacob, can you print your last result? I just want to see. Okay, so it's the same. Interesting.
Jacob, can you print their, let's see, np dot dot underscore, let's see, I think double underscore, yeah, dot, and then version, yeah. So that's your NumPy version. If everyone else wants to check what theirs is.
Yeah, mine's 1.17.3.
Mine is 1.15.4.
Okay. Well, that's kind of odd then. I thought both of you would have a newer or older version, but everyone's kind of all over the place. So it's probably related to that.
Inverse transform.
Could it also be the sklearn?
Yeah, it could be the sklearn too. So maybe try doing import sklearn and then sklearn dot version.
Mine is 0.20. How do I upgrade?
You should be able to do, let's see.
Isn't it just pip update? I have 0.21.3 on sklearn.
Wait, what do you have?
0.21.3.
Okay, so slightly different.
Mm-hmm.
Jacob, can I see your original M? Like before transform? Okay. Interesting.
So to upgrade, you can do pip install and then the package name, and then a hyphen and then a capital U in your terminal.
Okay.
So maybe try doing that on the NumPy and the sklearn, but that's still kind of weird.
Mhm.
Inverse transform. Hmm.
Well, so Beth and Bonnie, what happens if you just pass in your data frame into the inverse transform?
Pass df.
You'll have to do it like the same way that we did the transform, like df and then brackets df column.
Df dot df column.
It's like what Jacob has there.
Okay.
So that should give you your original data back. So like GRE should be like 300. Yeah, that looks right there.
No, it doesn't. It
Mine-
still give me
It keeps the same thing.
0.84. Yeah.
Mine
Okay.
says columns is not defined because I have a bracket instead of a period. Okay.
Yeah,
mine
it
has
doesn't
the
work for me, this one.
Mine has the transform data.
So the inverse transform doesn't work for me. Maybe that's because my version is too old.
Yeah, the first thing I'd say is try updating. Hopefully that works, because if not, then that's like a huge problem because I have no idea.
Mine are more up to
Okay.
date than Jacob's are.
Yeah, I was gonna say yours is newer, so
And same?
Yeah, and I'm having the same problem that you are, Bonnie. So let's see. Inverse transform sklearn update. Oof. Oh, and I don't like